What's up? Sorry for suddenly cutting off. But yeah, okay. We were talking about mixing. Let's start with some acid 1 plus acid 2. So the formula for this will be N1V1, this is normality, plus N2V2. We studied normality in a previous video. N1V1 plus N2V2 upon V1. Okay, now you can also write this as gram equivalence of 1 plus gram equivalence of 2 upon V1 plus V2. Yeah, okay, yeah, right, okay. Now for acid plus base, acid plus base, you get gram equivalence of, this is net normality resultant, gram equivalence of acid mod minus gram equivalence of base upon V1 plus V2. This is N1 V1 minus N2 V2 upon V1 plus V2. Yeah, right? Right. Right. Now, give me 1 second. Let me write down a question. I will erase all of this except this part. We can use that as a reference. We have already done sampling, no? God damn it. Yeah, alright. That's a waste. The fuck is my pen? There it is. Alright. Question. You have 0.1 normal HCl of 100 milliliters volume, and you have 0.2 normal CaOH whole twice upon 50 milliliter 50 milliliters of this. Now when you mix these two, okay, mix, what will be your end resultant? Alright, I have given you enough time to do this. This is simple, just formula based question. 0.1 into 100 into, plus 0.2 into 50 ml upon 150 ml. So this will be, this is normal, okay, N1V1 plus N2V2 upon V1 plus V2. So this will be 10 and this will be also 10 upon 150. Sorry, I mean this should be minus, right? Yeah, I'm sorry, so sorry. This will be minus. So 10 minus 10. 10 minus 10 upon 150 is just 0. So n resultant will be 0. And that's it. Huh? That's it. Now, I'll give you a massive question, massive. You know what else is massive? The low table fade. God damn it. Alright. Question. You have m by 10 plus 100 ml. I mean m by 10, 100 ml, 100 ml of of I don't know, anything, okay, of anything. Now you add 20 milliliters of H2O to this, yeah, then you will get an end resultant. Now you take 10 milliliters out of that, then you have to find number of moles of H2SO4. Number of moles of H2SO4. Now you mix with this another solution of m by 100 5 ml CaOH whole twice, and then you will get an end resultant. Now find this, and this. Yeah, should be easy enough, right? So I think we had enough time. Let's start our answer. Yeah. So first we have to find normality of this solution plus 20 ml. So what is normality? Good question, that is. Normality equals to molarity into n factor. We have studied n factor, we have studied molarity. Okay, so now we have to find molarity of that. Okay, so let's find that out. So molarity is, what is molarity? Insane question, you should be knowing that. Molarity would be, how the hell am I supposed to write this? 10 upon 120. Yeah. You can do something like this. 1 by 10. How do I write this? We already know the molarity though. Give me 1 second. Yeah, so we have to find the change in molarity. Of course, you are adding plus 20 ml, so of course the molarity will change. So this is a case of dilution. So what is the formula of dilution? Dilution's formula is, it is m1 v1 equals to m2 v2. Not sampling, dilution. M1 v1. This does not look like m1 v1, so we'll have to find m2 v2. We know that m1 is m by 10, which is 1 by 10. v1 is 100 ml, so this is 100, so this will be 10. m2 v2 is, let's take this as H2SO4 because we need to find n factor. H2SO4, yeah, that should be fine. This is m2 v2, so v2 is 120 ml because we are adding 100 plus 20, so 120 ml. So 10 by 120, this will be 1 by 12 equals to M2. So the molarity of this liquid is 1 by 12. Now if we multiply that by 2, the n factor, normality is molarity into n factor, so this will be 1 by 12 into 2. 2 is the n factor of H2SO4. Yeah, 2 is the n factor of H2SO4. So this will be 1 by 6. So we have found the first n resultant. So n resultant 1 equals to 1 by 6. Now we are sampling 10 mLs of H2O, H2SO4 from that normality. We are sampling. So sampling is N1V1 equals to N2V2, because this is a case of sampling. So yeah, we can find the number of moles in V1 by just putting it into the formula. Yeah, M equals to N upon V, right? Am I right? I think I'm right. I really think I'm right. Or am I wrong? I don't know. Anyways, we know that this is 1 by 12. This is M1. So 1 by 12 equals to N2 upon V2 is just 10 milliliters. Right? 10 milliliters. And this is in liters now. So this will volume 2 in liters. So this will be multiplied by 1000. So 10 by 12 into 1 by 1000. That's N2. Number of moles into. So that will be 1 by 1200. That is the number of moles. 1 upon 1200. Yeah. Now we have to find the end resultant when we add more to this. Yeah. I'll erase this up. I mean, I do have space on top, but who the fuck needs space on top? Ayo. So we know that this is a case of mixing a acid plus base case. Yeah, so we know the formula to that: N1V1 minus N2V2 upon V1 plus V2. Yeah, so N1V1, N1 is, what is N1? The normality of this. Normality is molarity into n factor, which is just 1 by 6. Yeah, normality does not change on sampling. I should have remembered that, no? 1 by 6 into volume 10, right? Yeah, I think I'm right. Minus, what is normality of 2? This normality is 1 by 100, right? Or am I wrong? Maybe I'm wrong. Maybe I'm just doing this all wrong. Maybe I'm dumb. Maybe I'm very dumb. That I am, though. That is true. Anyways, what is N2? Normality of this. Molarity into n factor. So that is 1 by 100 into 2, that is 1 by 50. So 1 by 6 minus 1 by 50 into V2, 5, right? That's 1 by 10. And 1 by 6 minus 1 by 10. sorry, 6 by 10 minus 1 by 10. That's 1 by 2 upon v1 plus v2, 110. Am I doing something wrong? Sorry, 15. 1 by 30, right? Or am I wrong? Maybe I've done something wrong. What is normality of this? Normality is going to change. Am I dumb? Maybe I'm dumb. Number of moles upon weight in kgs. What is molarity of this? Molarity will be the same, nah? No, molarity has changed, I think. Or molarity is the same, I don't know. Honestly, I don't know. Just take this as the answer. If it is something else, comment down below. Well, it could be 20 as well. It could be 20. But anyways, we have to continue our topics. I'm making a lot of mistakes today, I guess. But that is of no matter. Because we are starting redox reactions. What exactly are redox reactions? We'll study that. So redox. So finally a new topic. And the third topic of mole concept that we were going to learn. We finally here. It only took 5 lectures, I think. Reduction plus oxidation is known as redox. Yeah? Yeah. So, star point. Oxidation. I should have different colors, no? That would look much better. But I do not, unfortunately. So you'll have to stay with this. So, what are the ways of oxidation? Now, we don't really need to know why, but for now, just know what is oxidation. So, gain of oxygen is, of course, oxidation. Loss of hydrogen. Loss of electron. Increment in oxidation number. We'll study what is an oxidation number. I'll give you some easy formulas too. Oxidation number, addition of electronegative element, and sixth, removal of electropositive element. Yeah, all right. Now this basically means the same thing. This means the same thing. These two mean the same thing. Loss of electron also means loss of electron means increment in oxidation number. Why do these two mean the same things? So we know the order of electronegativity. I have made you study that as well. Yeah, study that in a physical previous class. Novelty order. See, so the order goes like F is greater than O is greater than N. Yeah, FON. Yeah, FON CL BR, I think. Phone call bruh. It's something like this, yeah. Phone call. These are almost the same. Phone call bruh. iodine, sulfur, carbon, phosphorus, hydrogen, boron. So this is the order of negativity. So fluorine is the most negative and boron is the least negative. Yeah. Now we'll study oxidation numbers, I think. Do I need to give you example of these? I don't think so. Yeah, no. I don't think I need to give you example of these. We can study reduction now, I guess. I mean, what is there to give an example of there? I mean, I could show you some reactions, but who really wants to do that? Removal. I mean, sorry. I need to put the topic in first. Redox. Sorry, reduction. So we can say number one, removal of oxygen. This is basically inverse, yeah, to gain of hydrogen. 3, gain addition of electropositive element. Removal of electronegative element. Addition of electron. Yeah. Now, how do we find oxidation state or reducing agent or oxidizing agent? We have to study that, don't we? I guess we have to study that, but haven't you studied that in 10th too? You have studied that in 10th too. So, I'll teach you anyways, okay. But I'll not go very deep into it. I just needed to remind you what oxidation and reduction was. The one getting reduced is the oxidizing agent, and the one getting oxidized is the reducing agent. Yeah. Redox, redox. You can keep that. Reducing agent and oxidizing agent. I'll give you one example, I guess. H2 plus O2 equals to H2O. Yeah. This is getting oxidized. This is getting reduced. Why? Because this is having an addition of hydrogen. Hydrogen is having an addition of oxygen, which we know is oxidation, and H2 is getting added to oxygen. This is making the oxygen reduce. So when something is getting reduced, it is the oxidizing agent, and this is the reducing agent. As simple as that. Next topic. What the fuck? Reducing power. The the tendency to reduce something is called reducing power. Oxidizing power. The tendency to oxidize something. What's the time? I don't know. Next, we get on to oxidation state or oxidation number. Now this will actually take some explaining. Yeah, this will actually take some explaining. Now let's say you have a compound like this. NH3. Now we know that I have made you study this too. Oxygen forms a bond with hydrogen, which is partly towards its side because it's more electronegative. Yeah. Now this is the same. Yeah. So when you break this bond, a -1 will come here, a +1 will come here, because nitrogen is more electronegative than hydrogen. When you break this bond, another -1 will come here. When you break this bond, another -1 will come here, and there will be +1. So see, the oxidation number will be of nitrogen will be -1 -1 -1. So this is -3. Yeah. So this is how you find out the oxidation number. We can write a definition for this. The imaginary charge developed on an element when molecule is considered to be 100% ionic. So that is the definition. Now let's do some problems on this. I will give you a structure. You have to find out the oxidation number. Where is the camera? There it is. Okay. First example, NaBH4. So we can ionize this in Na plus and plus BH4 minus. We know where this comes from, but yeah. So this is B H H H H, and there is a -1 already here. So when you break this bond, a -1 will come. No, boron is less electronegative than hydrogen. So when you break this bond, a -1 will come here and a +1 will come here. When you break this bond, it will develop a +1, this will develop a -1. When you break that bond, +1, -1. And when you break this bond, +1, -1. So the oxidation state of this is +1, +1, +1, +1, -1. So +3. +3. Yeah. Yeah. Next, H2SO4. We have to find the oxidation state of S. The structure is as follows. So how do you do it with double bonds? Yeah. When you break this double bond, a -2 charge will develop here. When you break this double bond, a -2 charge will develop here. Cool. Sorry, sulfur is less electronegative, so it will be +2, +2, -2, -2. When you break this bond, +1, +1, -1, -1, -1, +1, -1, +1. So oxygen will be -2. I'll just write down all the elements. Oxygen -2, and sulfur +2, +2, +1, +1, 6, and hydrogen +1. Yeah. Yep. Cool. Yeah, that is all for this one. For oxidation state, well, it is not all for oxidation state, because let me give you one formula. Actually, before I give you a formula, I need to make you study a lot more shit. The board has gone blue. Crazy. Yeah, crazy. So H, hydrogen with metal, with metals, it gains a -1 charge. Okay, and the metal will of course gain +1 charge. With non-metals, because usually metals are more electropositive than hydrogen, so hydrogen is relatively less, I mean more electronegative, so that's why it develops a negative charge. With non-metals, it develops a positive charge, H plus O minus, positive with non-metal. Now oxygen has many different oxidation states. Yeah, many different oxidation states. There are a whole lot of oxidation states actually, so I'll have to make a huge table, huge massive table for this. Okay, all right, give me 1 second, let me set up, because I'm getting kind of tired of sitting, so I'll lay down. Yeah, okay, I think that should be fine. Now let's write oxygen. Yeah. Now first, actually, let me just draw all the lines before I start. 2, 3, and a 4, 5, 6. There are 6 types actually. 6 different 6 different oxidation states for oxygen. Alright, let's start with the left as possible. So the first and the most common -2. This is for oxides. That is why it's the most common, because oxygen mostly forms oxides. Next is -1. This is for peroxides. You might have heard a name, H2O2. So this is just hydrogen peroxide. It has a peroxy bond. So this is what it looks like. This is what it looks like. There is a single bond between this and that. So when you break this, neither of them are more electronegative than the other, so this will develop no charge. And when you break this will develop a -1, and when you break this will develop a -1. That is why the oxidation state is just -1. Yeah, all right, hopefully you've understood that point. Next is -1/2. -1/2. When the hell does this happen? Well, it's just called superoxides. Yeah, don't worry when it happens though. Don't worry when it happens. For now you don't need to worry about that. Now 0 is just molecular oxygen. So oxygen, ozone, yeah, those two. Now plus. Now when will oxygen develop a plus charge? Oxygen will only develop a plus charge when it is connected with fluorine, because fluorine is the only more electronegative material than this. So it will have F +1 when O2 F2. So basically two O2s, O2 F2. So this will be the bond. When you break this, no charge will be developed. When you break this will get a +1 and this will get a -1, because fluorine is more electronegative than the oxygen. Same here. Now final +2. When will it have +2? Well, when it has FOF. So this will be the structure. Break this, break that, +1, +1, +2. Also you can draw the structure like this. But we'll learn how to draw structures in bonding. There's a chapter based on bonding. Yeah, I know, crazy. No, what the hell is a superoxide? A superoxide is a O2 minus. Yeah, a bottle fell. Give me 1 second. God damn, that leaked. Shit. I'm going to draw the structure here. Yeah. Now we do have a formula to figure out the oxidation state, so you're not totally fucked. Yeah, you're not totally fucked. Yeah, this was the only cloth I could find, but I don't know where my glove went. So yeah. Next up, is the formula. Formula for, now this will not work every single time, but it will work most of the time. Formula for finding oxidation state. I will tell you when it doesn't work. So there is a simple formula. AXBY. You might be getting flashbacks from physics, but don't worry. We have not studied physics on this channel yet. That's going to be the next chapter. I'm thinking I should start with vector here. Equals to A. Oxidation state of A equals to A. Let's say that. And oxidation state of element B equals to B. Let's say that. So AX plus BY Z. Z is the charge, okay? AX plus BY equals to Z. Now what the fuck does these mean? So let's take an example to see clear that confusion up. FeSO4. Now this is 0, charge is 0. Fe is plus 2, but we don't know that yet. So let's figure out what will be the oxidation state of Fe. We know that SO4 is made up of a sulfur and 4 oxygen. SO4. Now a sulfur max oxidation state is 6. So we take the max oxidation state, yeah? Fe plus 6. Let's say this is X. So X plus 6 plus oxygen. Oxygen is minus 2. 4 into minus 2 equals to 0. So this is 6 plus minus 8 equals to 0. Minus 2 equals to 0. X minus 2 equals to 0. And X equals to plus 2. So the oxidation state of FeSO4, specifically Fe in FeSO4, is plus 2. Yeah? Alright. More examples? Give me 1 second. Let's write a note here. Now we'll just say this formula as a note here. In a literary ways. Sum of oxidation states of each element in a molecule is equal to the net charge present on the molecule. All right. Next, what do we have to do? Let's discuss some first group elements, oxidation number: H, Li, Na, K, Rb, SCS, Fr. Now for all of these, it is going to be plus 1. For second group, B, E, N, G, C, A, S, R, BaRa. This will be plus 2. This is called the S block. We'll study the S block in, I think, this 11th. Now P and D block have SPDF, no, has variable oxidation states. Oxidation state or oxidation number, they both mean the same thing. Yeah, hopefully you have understood that. Now, where does this formula not work? Yeah, where does this formula not work? Give me 1 second. Let me erase this. Boom. I'm dirtying my hands for you guys, huh? I'm dirtying my hands for you guys. So, H2SO5. Let's find the oxidation number for S in this. So, we'll use the formula 2 into 1 plus x plus 5 into 2 minus. This will be minus 8, x minus 8 equals to 0 and x equals to 8. Cool. But let me write the but the highest oxidation state for sulfur is plus 6. What the fuck? What the fuck? Huh? What do you mean? How is the oxidation state of sulfur greater than its maximum oxidation state? That is just not possible. So this is where the formula does not apply. And there are many other elements or compounds like this, H2SO5, where this will happen. Now, if this happens, which in most cases you won't have happen, but if this happens, note, let's write down a note. So, first note, if calculated oxidation state is greater than maximum oxidation state, then peroxide bonds are formed. What are peroxide bonds? So we saw in H2O2, this is hydrogen peroxide. This can be made like this. Now this bond between oxygen and oxygen is called a peroxide bond. Or a peroxy bond. Okay, so that's where the word comes from. Now let's see this note with an example. We took the example of H2SO5. So let's continue with this example. So we know that sulfur makes bonds with oxygen like this. Let's make this just like the H2SO4. Makes with bonds like oxygen like this. Now it makes one bond here, and one H here. But you can't put an H here though. Why not? Because, well, you won't satisfy the number of oxygens. So you need to put an extra oxygen here, and then you have to add the H. So this here is a peroxy bond or a peroxide bond. Now, now let me give you another element. Let me give you another example. CrO5. Now let's find the oxidation state of Cr here. So this will be plus 10. Yeah, but the highest, the maximum oxidation state for chromium is +5. Oh shit. Yeah, that's a shit. I mean +6, I think. Yeah. Yep. The highest oxidation state for chromium is +6. Okay, so let's draw the structure. This is what the structure will look like. Now this is in chemistry terms called a butterfly structure. I know you see something else. If this was a circle and this was a circle and then you join something, yeah. Anyways, uh, I'm sorry about that. Okay, maybe you don't know what I'm talking about, which would be very good, but yeah, this is called a butterfly structure. Now chromium for this will have +6 because one will be induced here when you break this bond, one will be induced here, one here, +2 up here, +1 here. So when you add this, +4 +2 +6. All right. We still have a lot more to study, so we better get to working on it. Well, I should be working on it, because we still have a lot of things to study because I'm teaching very slow. We are 52 minutes into this and we are basically not even close to being done yet. Okay, yet. All right. Number of peroxide bonds. How do you calculate the number of peroxide bonds? It is equal to n/2 into calculated OS minus maximum OS. OS is oxidation state. N is the number of atoms of unknown element. Elements. Okay. Now let me give you some elements and their maximum oxidation state. You should learn this up. Element max OS. Let's get one. Sulfur, which is +6. Chlorine +7. Bromine +7. Iodine +7. Phosphorus +5. Nitrogen +5. Iron +3. Chromium +6. Manganese plus 1. You have to learn that up. You can pause the video and write it down. Oh shit, I didn't mean to erase that. Give me 1 second, let me write that down. Now if this comes out to be an integer, actual oxidation state equals to maximum oxidation state. Now if this comes out to be a fraction, number of peroxide bonds will be higher integer and actual oxidation state will be max oxidation state minus 1. Yeah, cool. And now we can go to fractional oxidation states. Yeah, we are almost done here. I mean, not really done. We are almost done with this lecture. Yeah, I have still a lot of things to study. I mean, make you study, teach. I have a lot of things to teach. All right. All right. What is the time? It's 00:35. Goddamn. I'm sleeping late, I guess. Well, anything for you guys. Well, for myself, to be honest. But yeah. Now, for the first example, Fe3O4. Now, when you calculate the oxidation state for this, it will be 8/3. Fe will be 8/3. But how is that possible? How can an oxidation state be 8/3? Well, this is the average oxidation state. Yes, average oxidation state. What the fuck? Average oxidation state? What do you mean by that? Well, Fe3O4 is made up of two elements, FeO and Fe2O3. Yeah? Now, FeO has a +2, Fe2O3 has a +3. Two atoms with 2 plus 3s. So, +2, +3, +3. Now, if you take an average of that, that will be 8/3. Yeah? Because when you add these, you have to divide by 3. And yeah, that's why. This is the average oxidation state, and this will be individual oxidation state. Yeah? Now, let's take another example. My whole hand is going to be blue at the end of this. Pb3O4. Again, 8/3. This is PbO2 and PbO. No, give me 1 second. 2 PbO? I don't know. I'm forgetting. I know this though. +4 +2 +2. This is the arrangement. I don't know how it's made. Is it PP2O3? No, can't be, right? No, can't be. PP2O4 can be. That can be, yeah. One is PP2O4. No. No. PBO. How does that sound? That's plus 2. PbO2, that is plus 4. But we don't have the enough oxidation for it. It's something, okay? It's something. Okay, it's something. I'm forgetting. Give me. I'm stupid. Right. This is plus 4, plus 2, plus 2. That I remember. I don't remember how it is though. Now Br3O8. This will be 16 by 3, the average. Now the structure of this is Br, double bond O, 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 double bond O. So this is plus 6, plus 4, plus 6. So 16 by 3. Cool. Do I need to give any more examples? Honestly, no. Alright. Now let's go to naming, yeah? Let's go to naming. Naming is naming in redox, yeah? Naming of oxo acids. Now we have to divide this into two parts. Yeah, we have to divide this into two parts. One where max OS minus 2, and one where it is maximum oxidation state. One where the element is at the maximum oxidation state, one where it is maximum oxidation state minus 2. So at the maximum oxidation state, it is oic acid. Okay, oic acid. If it is at maximum oxidation state, so phosphoric acid, for example. Now, when you multiply the formula unit by 2 and subtract H2O, you will get per dash oic acid. Yeah, pyro. Okay, sorry, this is if you add one oxygen to it. If you add one oxygen to it, you will get peroic acid. Now if you multiply by 2 and minus H2O, you will get pyro dash oic acid. Now if you just subtract H2O, you will get meta oic acid. Okay, now if it is maximum oxidation state minus 2, first without any changes, us acid dash us acid. Now if you add an oxygen to this, I mean